In this video, we're going to concern ourselves with the Wohl degradation reaction, or degrading. So if something degrades, what does that mean to you? Well, that means it kind of breaks down, right? The same thing is going to happen here, but the sugar is going to kind of break down. Now, when we say break down, what do we mean? Well, we mean lose one carbon out of the backbone. So the Wohl reaction is actually the reversal of the Kalani-Fisher reaction. Kalani-Fisher elongates a chain by one, and the Wohl reaction takes away the carbon chain by one. So we need to figure out, just like we did with Kalani, what kind of reagents are required and what do these reactions kind of look like. Now again, we're going to concern ourselves with the aldoses only. We're not really going to be looking at ketoses at all. So that means if I have a hexose in the beginning, if it undergoes a Wohl, it will be a pentose in the end. If I have a pentose in the beginning and it undergoes a Wohl, then that will end up being a tetrose as a product. So let's take a look at the shorthand, I guess you could say, for the Wohl degradation. So we're looking at a sugar, and we're going to take this sugar and we're going to react it with a reagent. This reagent that we need is basically hydroxylamine. So we're going to put trace acid. So just a little bit, that's all that we need, and then hydroxylamine. Now hydroxyl is an OH group, right? And an amine is an NH2 group. So this is something that you should know. We've looked at this hydroxylamine before. We've seen that already. So hydroxylamine is a structure that you should have memorized because that could show up on a test, right? This whole structure, what is the structure for hydroxylamine? It's NH2OH, hydroxyl OH, amine NH2. So this is kind of the first round. We take trace acid, we take the aldehyde group, it reacts with the hydroxylamine, and it forms an oxime. So I'm just going to put that up here at the top. This is a word that we've seen before too in the past with the carbonyls. I'm not going to go into it, but that is something that we've kind of seen. So we do see an oxime that gets formed. In the next step, so this is step number one. In the next step, we bring in yet another set of reagents, and these reagents are basically nothing more than acetic anhydride. So ACETIC anhydride. Now, we've looked at anhydrides before in the past. You should know what an anhydride is, and you should know the structure of acetic anhydride. I'm not going to do that for you. You should know that already, so we're going to keep trucking on. If you don't know what that is, I would highly encourage you to take a look at that structure. Acetic anhydrides we abbreviate as AC2O. So that means two acetate groups combined with an oxygen. That's really what that is after. So that's the shorthand representation of acetic anhydride. So we take acetic anhydride and we heat it up to boiling. So 100 degrees Celsius, boiling point of water. So once this thing begins to boil, we then add our third set of reagents to the system. And this third set of reagents will include OH and water. So if you go back and you compare this to the Kalani-Fisher, okay, Kalani-Fisher started off with acid and a nitrile group. This starts off different. It starts off with hydroxylamine, kind of a base if you want to think about it. So Kalani-Fisher somewhat starts off with an acid. Wohl degradation is backward. So this starts off with a base. In the second step of Kalani-Fisher, we went H2 and palladium. In the second step here, we do acetic anhydride and we heat it up super hot. And then in the third step of Kalani-Fisher, we ended up with acid again. However, in Wohl degradation, we're ending up with a base. So again, backward. It's the opposite of. So this is the Wohl kind of outline, and we basically shorten the carbon chain because of it, right? That's all that the Wohl degradation is going to be doing. So let's take a look at an example. And the example is going to come straight from your text, and it's going to say, okay, well, what sugars could be made from the Wohl reaction of D-ribose? Okay, so that means I need to take a look at D-ribose. This is probably one that I should remember, right? Because we said ribose is going to show up much later on. I probably need to know the structure of D-ribose. That's probably going to be important. So as of now, if you don't know the structure of D-ribose, then that means you're going to have to look it up in the chart and find it. So that's kind of the first step of this question. I need to find D-ribose, and D-ribose is an aldose. So we start off with this C double bond OH up at the top and this CH2OH down at the bottom. And if I look at ribose, I'm going to see 3 carbons on the inside, and all 3 of these have their OH groups to the right. So there's the structure for D-ribose. Can't get simpler, right? All of them on the same side. D-ribose is a pentose. There's 5 carbons there. So when it undergoes a Wohl, it will end up being a tetrose. One of these carbons will be deleted. The question that we have to ask ourselves is which carbon will disappear, right? And it's always going to be the top carbon. So in the Kalani-Fisher, we added the carbon at the top between the carbonyl and the carbon that was there. In this one, we're taking away that carbon. So the carbon that we are going to remove is right here. That's what we're after. Okay, so again, this sugar is going to react with hydroxylamine. Then that product converts and reacts to acetic anhydride. And then that product reacts in a basic environment. All of my OHs go exactly where they were. The only difference is that this carbon is going to be deleted. So that means that my structure is going to look like a C double bond OH and then CH2OH here. This carbon goes away, and we're left with an OH to the right, and we're left with OH to the right. Okay, so what sugar is that? Okay, well, this is another structure that I should know. This is now a 4-carbon chain, and those 4 carbon chains that have the OH group both to the right-hand side, well, this is called D-urethros. So there's the structure of the sugar that is made, and there is the name of that particular sugar that is my product. Okay, now this is really it. That's all that there is to a Wohl degradation. Be careful though with the questions, because it could be like this one where it said what sugar is made from the Wohl degradation of D-ribose. Or they could play off on words a little bit, and they could say what sugars could undergo Wohl degradation to make D-ribose. And that's a different type of question, right? Here we've taken D-ribose, we've deleted a carbon to get a product. However, the answer to this one up here is a little bit more complicated, because they want to know what 2 sugars could we degrade in order to get basically D-ribose as a product. So that means they want us to start off with 6 sugars, because we want to end up with D-ribose in the end. We want to end up with a C double bond OH CH2OH, and we want to end up with all of the OHs over here to the right, and we want to know what two sugars would allow that to happen for us. So again, you go back to that sugar chart and you kind of figure out, okay, well, I know that I have to start with 6 sugars because the question wants to know what would I start with to get D-ribose. It's a different point of perspective. So I need to figure out, well, what sugars do I have in the list that have the OH groups, 3 of them at least, the bottom 3, on the right-hand side. Because if I degrade that, then I can get D-ribose as a structure. Well, if you take a look at those sugar choices that you've got, you do have 2 choices that meet that criteria. The first one is D-allose. And D-allose is going to have OH, and then OH, and then OH, and then OH. So if this sugar undergoes a Wohl, this carbon up here at the top gets deleted. And what you have left over are 3 carbons. All of the OHs are to the right, and that gives you D-ribose as a product. Well, I need to find another because it said what 2 sugars would allow this to happen. Okay, so I can go through the sugar chart again, and hopefully I'll be able to find another one that does something similar. And I do. D-altrose is the other one. So D-altrose has an OH group up here at the top to the left, and then the remaining 3 have the OH groups to the right. So if this undergoes a Wohl degradation, this carbon gets deleted, and I still have OH, OH, OH over to the side, and that matches the structure that I want here. So the 2 sugars that could actually make D-ribose under a Wohl degradation is D-allose, that's my first choice, and my second choice is D-altrose. Alright, so it's all about using the chart like we've seen before in all the previous examples. How do I use the chart? What do these structures look like? What's their relationship? How on earth do I start off with a reagent and end up with a product? And with the Kalani-Fisher or the Wohl degradation, it's all the same, right? I take a look at it. I'm either adding a carbon and it's got a choice of where it adds, or I'm taking away a carbon and I'm deleting it and getting rid of it. So that's all of the complications that we are going to see with the Wohl degradation or the Kalani-Fisher. We're not going to throw in monkey wrenches. We're not going to throw in strange and weird things for you, again, either on the quizzes or the test. The homework might be a little bit more involved, but once again, like we've said over and over and over, you've got the book, you've got the notes, you've got the videos in front of you to answer these questions with. So in the next video, we're going to kind of take a break on reactions for a minute, and we're going to go back to the structures of sugars and begin to look at what other kind of funny things that they will like to do to you. So just when you think that you have sugars under control, they're going to come around and they're going to play dirty. And we're going to see what happens to the structures of these sugars now that we've kind of talked about these open chained forms.